Okay, so this talk focuses on zoology of graviton non-Gaussianities during inflation, that is, how the graviton interactions depend on the way in which the de Sitter isometries are broken during inflation. So the outline is the following. We start with some motivations. We then review the Zoology of Condensed Matter paper, that is the paper upon which this work is based on, essentially. Then we discuss the coupling of the results of this work to gravity, and now then I will go on to discuss gravity and self interactions, some phenomenology. I will conclude then with some prospects. So some overview motivations. So inflation could have happened at a very early scale, 10 to the 14 GeV, and if this was the case, then this would offer an unprecedented window into high energy physics. The observables that we're interested in are non-Gaussianities of metric perturbation during inflation. This is what we can access at late times, and the reason why these are linked to energy physics is that interactions during inflation, they will leave their imprint into these non-Gaussianities. So from this point of view, we have that cosmological observables act in some sense as some cosmological collider. There are two ways that we can attack this problem of what happens during inflation. One can ask what are this. One thing one can do is ask what are the signatures of new particles during inflation. Or another way that one can proceed is recall that we're not in flat space, but we're in the Sitter space, and then some lessons we learned so far is that some phenomenological interested cases are always arise when some of the de Sitter isometries are broken. More precisely, the de Sitter boosts or the de Sitter special conformal transformations, more precisely, are broken. Okay, so I will focus on the second of these two cases, so I will not focus on new particles during inflation, but I will focus on the consequences of the different ways in which the Sitter boosts are broken. Whenever we break some global symmetry, we know that some Gaussian modes will be present. These Gaussian modes in principle can be a lot, so a complete analysis of all the possible interactions and the resulting non-Gaussianities is complicated. And so for this is why I decided to focus on graviton self-interaction. This is a simpler example to study. Another way why I decided to study this, another reason why I decided to study this is the recent developments in the Cosmological Bootstrap program. So in this program, what people try to do is try to obtain some set of rules to get correlation function and cosmological observables without referring to a Lagrangian. And recently there has been a lot of work to extend this program to the boostless case. So I think that working on the theorem of the Lagrangian, as I do throughout this talk and in this work, can still help to develop the bootstrap rules, can provide some theoretical data upon which then people can try to understand better how to develop the rules. And finally, a reason why also I decided to study this graviton non-Gaussianities is also that in principle, if one day these modern gravitational waves are detected, having classified all the possible observational signatures could be obviously very useful. Okay, so then let me go on to the review of the Zoology of Condensed Matter. So what we want to do in this work is to study how different symmetry breaking patterns of the Sitter group. But then we can do some intuition from working on subhorizons case and then work with the Poincare group. And this is what was done in this work, 2015. The authors there classified all the symmetry breaking patterns associated with a static, homogeneous, and isotropic medium. So homogeneous isotropic is very clear to understand why we want such a medium in cosmology. Let me spend a word on why we want a static medium. So the simplest way to understand this is by an example. One can look at the case of a speed of sound, Cs. So we want to be able to have the speed of sound to be much different from 1. However, and this is where we want a boost to be broken, but we don't want the speed of sound to vary a lot in time. And this is why we want staticity. When we go to the Sitter we go to cosmology and the sitter, this basically amounts to requiring that the sitter dilations are only softly broken. So let me quickly then review how one can obtain different symmetry breaking patterns by working with the generators of the Poincare algebra. So we have space-time generators, and also then we have some unbroken generators that govern the collective excitation of the system. For example, P bar naught here is total Hamiltonian. The different symmetry breaking patterns are decided by whether or not the space-time generators are equal to these unbroken ones, or if they are not equal, which of these Qi and Q tilde I are different from 0. These are internal symmetry generators. Okay, so depending on, as I said, depending on Q and Q tilde I different or not from 0, we have different cases. And then let me discuss here these cases. So I discuss different systems. The middle column contains the setup of the generators, while in the last column discuss the order parameter and the Goldstone modes for the simplest scenario, the one with the minimal number of Goldstones. For example, we have a type 1 superfluid, where the order parameter is a scalar field with a web that depends on time and one Goldstone. Then we have solids, jellies, and fluids. The order parameters here are the Lagrangian coordinates of the volume elements of the fluid or of the solid. Then we have a final temperature superfluid or supersolid, which is a mixture of the other two. And then we move to framids. These are a bit peculiar. You see that the translations are never broken, in the sense that Q and Qi are always 0. And the order parameters here are vectors, vector fields. Either we have one time-like vector field with a wave and 3 Goldstones, or 3 space-like vector fields with a wave and 6 Goldstones. The last case is a mixture of a type 2 type 2 framid and a type 1 superfluid. This is type 2 superfluid, and you see that this is the symmetry breaking pattern. So we already see that in this case there are two scenarios, type 2 superfluid and the supersolid or final temperature superfluid, which are a mixture of the other cases, so I will not discuss them in the following. Okay, so then let me go on to see how there is the coupling to gravity. So one can either proceed by gauging the Poincare group within the CCWZ construction, or we can just be a bit quicker and realize that in all our scenarios we either have a preferred coordinate system for superfluids and solids, or we have a preferred frame for the framids. So this means that we are either breaking the diffeomorphisms in the first case, or the local Lorentz transformations. So then what happens is that we can essentially, since we will have these additional degrees of freedom that arise from breaking these gauge symmetries, and these are essentially the scalar and vector modes that will be the Goldstones in the coupling limit, if you want. So what happens is that now we can use the broken gauge transformations to make the metric eat these additional degrees of freedom. That is, we are going to the unitary gauge. In this gauge, all the degrees of freedom are contained in the metric. Then, since we only want to focus on gravity interactions, it is trivial to do it, because in unitary gauge we only need to take the metric of this form, where gamma is the graviton, transverse and traceless, and we don't care about vector modes or scalar modes. Then what we need to do is to write down some operators using this metric that satisfy that do not break all the residual symmetries that are present. For example, if we were to break only time diffeomorphisms, we want to construct operators with respect to spatial diffeomorphisms and local Lorentz transformations. Okay, so now let me go on, and first I will first show how the symmetry breaking pattern of a solid, which is solid inflation, leading order in derivatives, captures the most general graviton interactions. And then from there I will go on and look at a few examples to get some phenomenology. So I will do so. I will do so by first looking at the different symmetry breaking patterns and showing that as I go through them, I can always have more and more freedom for the objects that I use to construct operators for the graviton. For example, let me start from the superfluid case. This is the EFT of inflation, essentially. So at lowest ordering fluctuations, we know that gamma here must appear with derivatives. This can either be time derivatives, and this essentially is the extrinsic curvature of the constant time hypersurfaces, or they can be two special derivatives, and this is the spatial curvature, that is the intrinsic curvature of these hypersurfaces. So when we go to the Framid, we have more freedom. So we still cannot build objects where gamma appears without derivatives, and the reason is that in unitary gauge, we are forced, whenever we try to write some object from the unitary gauge metric that does not have derivatives acting on it, since we know that this object, since the tetrad is normalized, we know this object will just reduce to cosmological constant. So we still cannot have gamma without derivatives, but we'll see now that there is a bit still more freedom than the effective theory of inflation. So first, let me emphasize that I focus only at type 2 Framid, only on that, because whenever I have a type 2 Framid, that is, I have a special tetrad, special dry-bine, in 4 dimensions, I can immediately construct the last vector to have a full Vierbein by using the volume form in this way. That is, this tells me that the Fermi type 1 is a subset of the Fermi type 2. Then, when I have this last vector of the tetrad, mu 0, I can use it to write down all the objects that reduce to the EFT of inflation operators when gamma only is considered. So we see that the EFT of inflation is a subset of this. And also now I have more freedom because I can use the dry-bine itself to write down some objects that have gamma appearing with only one spatial derivative. For example, this is one of them. So this is something that I couldn't do before. Finally, then, let me go to the solid inflation case. So then here I see that immediately I have even more freedom because what I can do is have gamma j appearing without derivatives. This already happens in the solid inflation case, where I have these 3 objects here, x, y, and z, that are essentially some traces of the spatial metric, and here gamma appears without derivatives. Then how do I reproduce the objects that I had in the other 2 scenarios? So I use this tangent vector O, mu, to the threading of space-time. This is a time-like vector that I can use to construct all the operators that I can have in the EFT of inflation. While the ones that I can have in the one particular to the type 2 Framid case, I can construct by using the one forms that are orthogonal to this vector. Then this is, for example, here you can see that I use some, one can see that one can construct these objects by, for example, using this gamma kij and so on. There are very well defined procedures to construct these operators. Okay, so let me go to some phenomenology. So now, essentially, in the solid inflation, we see the most generic graviton interaction. We can write essentially whatever we want. So it is a bit. It was not the purpose of this work to study the full possibilities, but only focus on particular cases. I will work in an expansion in perturbation and derivatives, and I will stop at second order in derivatives and third order in perturbation. That is, I will be able to describe up to the 3-level graviton by spectrum. So what is known from the solid inflation case already is that these x, y, and z operators, so the ones without derivatives on gamma, they will give me a graviton mass that is suppressed by slow roll, and also some cubic interaction that is without derivatives, and indeed this is not suppressed by a slow roll. This gives rise to some type of local non-Gaussianity, whose essentially was FNL depends on the number of e-folds of inflation. Then there is something new with respect to solid inflation, which is some new interactions at second order in derivatives. So what is the first thing one can think of doing at second order in derivatives? This is trying to change the speed of sound of the graviton. There are many operators that can change it. However, the important point here is not how many operators one can construct to change the speed of sound, but the fact that now it is not true anymore that the speed of that a modification of the speed of sound is univocally tied to some large interactions. This instead is what happens in the superfluid case. Whenever I change the speed of sound, I turn on some interaction and vice versa. So there, I could just redefine the light cone and immediately get rid of all the interactions for the graviton. Now this is not possible anymore because the interactions are, in some sense, detached, not linked anymore to modification of the speed of sound. You can see it here, for example. We have these two objects. Let's put gamma KL and gamma J here to delta KL, delta J. Then the objects then are just a quadratic contribution to the action of the graviton that modify the speed of sound. But I'm not forced to consider those operators together with these cubic ones. These can just be appear by themselves and just modify the interaction without touching the speed of sound. So this is a new feature of the case of breaking spatial diffeomorphisms. And also finally, let me emphasize that in this case also another consequence is that the fact that gamma here appears without derivatives, this will lead to a breaking of the consistency condition for a soft graviton. Okay, so then let me conclude. So what I've shown here is that essentially whenever we want to break the Sitter booths, we can just work on the setup of solid inflation, so where spatial diffeomorphisms are broken. This captures all possible interactions for the graviton. Now, an interesting prospect or line of research is the fact that all the free net we have could allow, in principle, to find some regions of parameter space where one can modify the tensor non-Gaussianities without strongly affecting the scalars, the scalar sector. So this, in principle, could be two regions of parameter space, but in principle they could be present. So this is interesting because this is difficult to do in single field inflation, in DFT of inflation. This is not very easy. One can only do it at very high order in derivatives. So at fourth ordinary derivatives, you can write some operators that can change the interactions of the graviton without touching the scalars, but not at lowest order. It could be interesting to see if instead this can be done at lowest order when you break special diffs. And finally, one interesting point is that this working at the level of Lagrangian could help with some shortcomings of the current boostless bootstrap approach, which are highlighted in this work, which are the fact that essentially, while these bootstrap rules can obtain the bispectra and the correlation functions of the fields under consideration, they usually don't have yet a way to understand which shapes, which parameters can be large and which shapes are forced to be small, and so on. So working at the level of the Lagrangian, as I've done here, could help in doing so. Okay, so I conclude here, and thanks for listening, and see you at the conference.